Good morning and welcome back to chemistry. What we're going to be looking at today are covalent networks. So this is the fourth type of substance that we're going to be looking at. We've looked at ionic, molecular and metallic. Now this one. So covalent networks are similar in a way to molecules because they have covalent bonds between the atoms. But these are going to be much larger. It's going to have hundreds and hundreds, millions of atoms connected together. So, covalent networks, they're solids, they're always solids, and they're chemical compounds made from a large network of non-metal atoms bonded together, just like in a molecule. Graphite, diamond, and fullerenes are all allotropes of carbon. So these are the three that we're going to be looking at. And they're just made from carbon atoms. So that's simple, at least. You say what they're made from. But they are in a different structure. So they might be arranged differently. So an allotrope means same element, carbon, but different structure. So diamond and graphite, they're both made from carbon, but they're extremely different. And then the other one we're going to look at is silicon dioxide, which is also known as silica. All right, so the first one, graphite. One moment. All right, so graphite consists of layers of carbon atoms. Each carbon atom is bonded covalently to three other carbon atoms. So here is one layer of graphite, and then there's another layer below it. In this one layer here, each carbon is bonded to three other carbons by covalent bonds. If you remember, covalent bonds are very strong. So one layer of graphite, extremely strong, but between each layers of graphite, they're only held together by weak intermolecular forces. So this layer can easily slide off that layer. That's why in a pencil made from graphite, when I move it across a piece of paper, what's going to happen is these layers are going to start sliding off and staying on the paper. That's what we see when we use a pencil. So, important thing to remember, each carbon is bonded to three other carbons through covalent bonds, which are very strong, but each layer are just held together by weak intermolecular forces. The other important thing to know about graphite is that you probably know that carbon always makes four bonds. It's got four valence electrons, it makes four bonds. But as you can see, this one here, it doesn't make four bonds, it only makes three bonds. So what it means is it's got one leftover electron, which is free to move around the graphite. Here it says delocalized electron. And if you remember from the metals, if something is conductive, for something to conduct electricity, it needs to have a charged particle which is free to move. So this is a charged electron, it's got a little minus by it, and it's delocalized. So what this means is that graphite can actually conduct electricity. Remind me when we get back to school, get a pencil and put some electricity through it and see what happens. It will conduct it. As far as the physical properties and chemical properties of graphite, graphite's got a high melting point. So in order to melt graphite, the strong covalent bonds between carbon atoms must be broken. And because they are strong covalent bonds, it will require a lot of energy. So graphite has a high melting point of over 3,500 degrees Celsius. For electrical conductivity, because each carbon atom has one delocalized electron, that electron has a charge and it's free to move. Therefore, graphite can carry an electrical charge. Soft and slippery. So, although the carbon atoms in the same layers are held together very strongly, In between layers, they're held together weakly so they can slide off each other. And it's insoluble, doesn't dissolve in water. That's because the carbon atoms are more attracted to each other than they are to the water. All right, so graphite is like a 2D structure, flat layers, while diamond is made from carbons, but in diamond they're arranged in a 3D formation. So each atom, each carbon atom is bonded to 4 other carbon atoms this time, and I guess they're in a tetrahedral shape. So each carbon atom's got 4 other carbon atoms coming off it in a tetrahedral arrangement. And this one is very similar. It's got similar properties to diamond. It's called silicon dioxide. In silicon dioxide, each silicon atom, these are the black ones, are bonded to 4 oxygen atoms. This one, they haven't drawn them all in, but that's how it goes. And each oxygen atom is going to be bonded to 2 silicon atoms. So you can kind of see in between each carbon, there's an oxygen there. Silica is, this is silicon, otherwise known as silica. Sorry, let's say that again. The silicon dioxide, SiO2. So for every 1 silicon, there's going to be twice as many oxygens. And it is found in, you know, those things they use, they sometimes put it in packaging, and it's called like silica gel or something, and it says "do not eat" on it. And it's usually used to keep things dry. That's silicon dioxide. It can also be used, you know, that really white squeaky sand. That really white sand is mostly silicon dioxide. So the properties of these diamond and silicon properties, they have similar properties. They both have very high melting points. So in order to melt them, the strong covalent bonds have to be broken because they're strong. And because they're strong, it requires a lot of energy, so they have high melting points. They are electrical insulators, which is the opposite of a conductor, so they don't have any free moving charged particles. There's no free electron to carry a charge, so it does not conduct electricity. Very hard, so diamond is the hardest substance known to man. So atoms are bonded by strong covalent bonds in a 3D tetrahedral structure. This means these molecules are difficult to deform and very hard. Just note that hardness and toughness are very different things. Diamond is super hard. You won't be able to scratch it with anything, with a knife, but that doesn't mean it's, sorry, let me go back. That doesn't mean it is tough. So if you get a hammer and you hit a diamond, it will shatter. That, if it's hard, it can still shatter. If you get something like a rubber hose is definitely, it's not hard, it's soft, but if you beat it with a hammer, it's not going to break. So a rubber hose is very tough but not hard, while diamond is hard but not tough. Because of the strong bonds and the 3D tetrahedral structure, that's why it is hard. And the next bit, that they are insoluble once again, and for the exact same reason. The attractions between atoms in the covalent network are greater than the attractions between the atoms and whatever solvent you're going to use, water or whatever. All right, and the last one we're going to look at, which I never seem to ask questions about, so maybe this year they're due to do it, are these things called fullerenes. And a fullerene is a hollow structure made from carbons which are covalently bonded together. So this one on the left, that's I believe that's C60. Are there 60 carbons there? Maybe. Anyway, this is the first one discovered was C60. So it's 60 carbons bonded together into a kind of football shape. are called Buckminster fullerene balls or buckyballs, but you can just call them fullerenes. And they also come in other shapes like tubes. So they're called carbon nanotubes, the tube versions of these. They have fairly similar properties to diamond and stuff. So firstly, high melting point for the exact same reason. Strong covalent bonds are holding the carbon atoms together. They are electrical conductors. Once again, it's got one free delocalized electron that can carry electrical charge. As you can see, there are three bonded to 3 carbons, so there's going to be a delocalized electron to carry the charge. They are soft and slippery. All right, this one's kind of confusing. This is they are actually discrete molecules. So there'll be lots and lots of these C60 molecules, and you know, maybe 60 carbons is bigger than a lot of molecules we see, but it's still tiny microscopic thing. So if you get like a bag of, you know, 100 grams of fullerene, what you're going to get is it's going to be like a black powder, very fine black powder. So the fullerenes are discrete tiny molecules in solid form, and this means they can easily move past each other. There aren't many attractions between individual fullerenes. This means fullerenes exist as a soft powder. They're soft and slippery. They sometimes use fullerenes as a solid lubricant because it's soft, but still solid. Last one, once again, like the rest of them, insoluble. Fullerenes are insoluble because the attractions between carbon atoms are greater than the attractions between the carbon and the water, or the solvent. All right. So that's basically that's what we're looking at. Sorry, just give me one moment. I've got to get this up on the screen. Right. So what I'm going to want you to do is there's 3 pages in the Scipad, I think, about these Buckminster these covalent networks. Sorry, let me get it up. All right, can we see this? Almost. Where have I got here? Nice. All right. All right. So from page 94 to 97, 4 pages I'd like you to do. Once again, the answers are generally here, where they talk about the properties. And you just have to explain it here and select which is right. Yeah, so just those 4 pages today, and I'll see you tomorrow. We'll find out today if we're going back to school next week, which will be exciting. All right, that's all for me today, and I'll see you tomorrow.